I need you to explain this.
I understand, Matthew.
Is that actually why it's the biggest?
I'm waiting for this. There we go. Okay, so we have the different elements here. We want to know which one's more chemically reactive. All right. We know that sodium and those things in column 1 are more reactive than the things in column 2. Okay, because the things in column 1, if they give away 1 electron, they're going to have the electron configuration of a previous noble gas. They also have a lower effective nuclear charge holding that electron in place compared to the column 2 atoms. Okay, so we've isolated it down to these 3. Now we need to figure out of these 3 what it is. Well, this has more electron shielding than the other. Actually, this is in column 2 too. So that one's out as well. So it's just between sodium and cesium. Okay. And this one has more electron shielding. So it's going to be easier to pull that electron off, making it more chemically reactive.
The question's a little different in here. It says reacts most quickly.
Irrelevant. It's
irrelevant.
Yeah.
It's the same.
It's the same answer.
Same reason.
Yep. And we actually did that lab in chemistry, if you remember correctly, where we put those metals in water. Most of you anyway, depending on
I didn't do it.
COVID protocols. All right. So like I said, group 1 metals are more reactive than group 2 because they have a lower effective nuclear charge. So as you go down the group, it becomes more reactive because you have additional electron shielding as you move down
What was literally breaking into my back?
periodic table.
She doesn't care now. Shut up.
Metals then are on the left-hand side of the periodic table. They're going to form basic oxides. Non-metals then will form acidic oxides. Elements in the middle then, your transition metals will can go either way. And then silicon oxide can be ceramic because that is a covalent network solid. And all right, so which of the following groups from the periodic table would be the easiest to oxidize? Okay. Oxidation involves the loss of electrons. So the group of elements that has the lowest ionization energy would be the easiest to oxidize, which is your alkali metals. Alkali metals are in this column. Alkaline earth metals are in this column. These are your halogens here. Your noble gases, which they don't have on this periodic table because they're talking about bonding, they're going to be your last column. And those are the 4 families that you need to be really familiar with their names. All right, we've talked about differences in electronegativities. So differences in electronegativities then lead to different types of bonding. So bonds in general are considered nonpolar if the electronegativity differences are between these values. Bonds that are considered polar then are between 0.5 and 0.7. And then anything greater than that is generally considered ionic. Now, typically for the test, I would know that this is 4. And then if you notice, this goes down by 0.5 all the way across the top. And then I know hydrogen is 2.1. Those are the only ones I know are fluorine and hydrogen. Those are the only 2 that I have memorized. And then I know that if I go down by 0.5, it's easy for me to calculate what these are. Okay, so I don't have them memorized, but I know, oh, it's nitrogen. I subtract 0.5, 0.5, that takes me to 3. then I know that as I go down here, that everything gets less. And that's it. That's all you need to know. That makes sense for the electronegativities? All right. So which of the following would be most polar? So most polar, this is a, let me see, fluorine is 4, so 3.5 is oxygen. Nitrogen is 3, and then carbon is 2.5. So the electronegativity difference here is 1. Hydrogen and oxygen, hydrogen is 2.1. Again, I have this memorized and this memorized. I had to figure these out, but it was easy, wasn't it? Okay. So hydrogen and oxygen, so 3.5 minus 2.1. 5 and 1 is 4, so that's 1.4. So that's more polar than that guy. 4 minus 2.1 is 1.9 for C. Kind of gotten off a little wonky here. This is 0.5 and this is 0.5. So C should be the answer. Right, but it's between a metal and a non-metal. So even though it's like highly, it's still going to be covalent because it's two nonmetals. They're going to share electrons. Okay. So C is your answer.
See?
CC? C. All right. Properties based on bonding. We have ionic here. They gave you a couple examples of that. They have given you that we know that ionic has high melting and boiling points. You guys have tried to melt salt before in here. Doesn't work. State at room temperature, all your ionics are solids. They are referred to collectively as?
Alkyl metals.
Nope.
Salt.
Salts. Yes. All ionic compounds are known as salts. Okay, it's not just NaCl, it's anything that's an ionic compound. In chemistry, we consider that a salt. It does not conduct electricity in a solid form. In a liquid form, which it would have to be really hot to happen, it would. And typically it's soluble in water, but not all of them are. You would have to look at the KSP values to be able to figure out if it's soluble in water or not, right? We talked about KSP. Remember KSP? Okay. You also know when you're talking about solubility with these ionic compounds that you have what?
Snap.
Snap. Okay. So all sodium, all nitrates, all ammonia, and all potassium. Not phosphorus, potassium. Okay. All right. So you also know that typically your heavy metals, like your silvers, mercuries, and leads, that most of those are insoluble. So the heavier the metal, typically the less soluble it is. All right. Covalent then, here are some of your covalent compounds. They have low melting and boiling points because they only need to overcome these IMFs. Typically, they are either liquids or gases, but you do have some of them that are solids, especially if they're bigger molecules, like sugar, for example. Sugar is a covalent molecule, but it's a very large molecule compared to, say, CO2. Okay, so because sugar has CO2, or C6H12O6, right? That's your sucrose or your glucose, okay? C11H22O12, I believe. That is your sucrose. This is like your table sugar. Because these are large molecules, they have high London dispersion forces because they have a high number of electrons, making them more
dense.
Isn't it? You
Negative.
You did the bucket of water thing.
Polar.
No.
Polarized.
Those are all non-polar.
More polarizable. Okay, remember?
Very dipole.
If you have a high number of electrons,
You have a higher chance of
then it makes the molecule more polarizable, leading to higher IMFs, which gives it the ability to be a solid at room temperature. So that's what they're talking about here.
That example of where one had hydrogen bonds, or one had dipole, one didn't. Yes.
Okay. It is not, a solid does not conduct electricity. The liquid doesn't either. Pure water, actual pure water does not conduct electricity. Okay. And you're like, but they always tell us not to mix water and electricity. That's because you're not usually working with pure water. Okay. So, and then is it soluble in water? It depends on how polarized the molecule is. So the more polar a molecule is, the more likely it is to mix in water. Okay. So for example, this guy, you're going to have some oxygen that has hydrogen bonding going on with that guy. And that's going to allow your sugar to mix in with water, which makes your Kool-Aid.
Yes.
All right. Network covalent bonds, then diamond, graphite, and SiO2, so silicon dioxide, are typically the ones that you'll find on the test. They will try to trip you up with this. I tripped you up on your IMF test, I believe, with one of these. If you remember back to like Unit 2 test, because you had a network covalent solid in there, and you had to figure out why that ended up with a higher boiling point. So very, very high boiling points. States typically are solids at room temperature. Does the solid conduct electricity? No, except for graphite. The liquid, typically it would have to be so hot that you're not going to get to that point, and then they're not soluble in water. Metallic, then, examples of metallic bonding, high melting points, typically, although some of them have lower ones like gallium. Most of them are solids at room temperature. Mercury is one of your exceptions, but we don't really come in contact with that anymore because its vapors are poisonous.
The liquid. So funny.
The solid then will conduct electricity. You've got copper wiring, and the liquid will conduct electricity, and then typically not soluble in water. Okay. All right, metallic solids then, when we have characteristics of these, we would have alloys. So this is a substitutional alloy. Your substitutional alloys have atoms that are very close in size to the atom that it's substituting. Okay. These are interstitial. These holes in between the atoms are called interstices. And so this is an interstitial alloy where you take a smaller atom and you fit it in there. When we talk about electricity, then we've got electrons that are surrounding the atoms, and they can become delocalized. So they can actually flow through the material, which is your electrical current. Metallic properties, then, they tend to be malleable, and they are also ductile, which means that you can pull them out into thin wires. And that's because you can move these electrons around and be able to shift them, thus allowing these atoms to be able to move and bend. Okay, so here are your substitutional alloys. You've got your, where you've got approximately the same number of radii or the same size. Crystal structure of elements should be about the same. You have very little disruption then, and it results in a solid, which remains malleable and ductile. They tend to have similar densities. Interstitial then, you have one that fits inside the other. So you have a very large atom, and then you've got other ones that are smaller, like your iron and your carbon, which is smaller, that are going to fit inside those holes. These are the only two that you really need to know about in terms of the AP exam. They do have something called intermetallic, and they've got heterogeneous, where you've got multiple phases going on. But the first two are the only two that you really need to concern yourself with. All right, so here's your question. Is this the next one in your packet?
Yep.
Okay. So we've got pure silver. Typically, pure silver, and gold is the same way, is usually too soft to form useful objects. So they will typically alloy it with either copper and or gold. 2 alloys of silver were created with equal amounts of silver alloyed with either copper or gold. If the silver-copper alloy is harder than the silver-gold alloy, which of the following would best explain the difference based on this table up here? Do silver and gold have similar radii?
No. Well, yes, it's similar.
It's the same value. Okay, making them easy to alloy. Silver has a higher electronegativity than copper, making the alloy tougher. Copper has a smaller radius than silver, disturbing the crystal structure and making the alloy harder.
Yes.
Or gold and copper do not have any oxidation states in common, making the alloy softer.
C.
You think it's C? Okay, let's check. C is the correct answer. Okay. When there's a significant difference in the size, the crystal lattice will be distorted, making it more difficult for the crystal structure to shift and making the thing harder. So the copper and the silver lattice will pin the lattice in place around the copper, preventing the movement. And that's what they do as far as steel. When they have steel, they have iron, and then they have carbon that's placed in there. And that's why steel is so much stronger.
So, interstitial?
Interstitial, yep.
So the copper fits in.
In this one, it's the copper that fits in between the silver. Okay, but in terms of steel, it's going to be the carbon and iron.
But copper almost has the same radius.
It's enough different that it's going to kind of lock this in place.
Jaden, come on, you're trying to picture a 3D image.
What did it say? Did it say something up here? I thought it said 15%. So more than 15%. So what is that? 128. 128 minus 144 divided by 144. So it's 11%. Yeah, I mean it's not as big as they said on the previous slide, but I guess it's enough to make it work. So all right. One type of semiconductor is germanium. Adding some impurities can increase the conductivity of the semiconductor. Adding which of the following would create a p-type semiconductor with increased conductivity? I think they took that doping out.
I didn't know how to do
Yeah.
Yeah.
I thought it was
This
DNA
is
metals.
something 3 valence electron something.
I just
I don't even know what gallium's.
Isn't gallium the one that's kind of like liquid?
Yeah, if you
Yeah.
warm it up.
I said that.
Oh, I didn't even know how to do this one.
Yeah, just give me a second to look it up, okay?
So how much for the chocolates too? What kind do you have? I have dark chocolate and mocha. Never mind. I'm getting two ones that nobody wants to buy.
I love dark chocolate.
Are you gonna buy dark chocolate?
If you save me dark chocolate, I don't know
I'm
you.
gonna buy chocolates. Okay.
If you keep me at least one, I'll buy at least one. If you have more, I'll buy more.
I love dark chocolate. It's the better version of everything else.
Okay, so P doping is a semiconductor in which is due to the movement of positively charged holes. N doping is due to the movement of extra electrons.
So you need a positively charged molecule.
Well, I searched it up and it said to make a P-type you need like an element that has 3 valence electrons.
Okay,
And N-type would be like 5.
okay.
So it has to have fewer electrons than germanium.
So that makes sense because it would lose electrons or gain electrons, right? So D is going to be the answer, which is gallium. So silicon, phosphorus,
They all have more electrons.
germanium,
Gallium's the one that has less electrons.
and gallium. Yeah. So, but that one would lose the 3. So that would make sense, right? I mean, based on what you just said, that one would make sense. Okay. I think they pulled this out of the test, this doping stuff.
Is this part of the curriculum?
I think they pulled it out.
We didn't study it, so.
All right. All right. So, what did you have for your packet next? Is there a next question here?
We have sodium chloride and magnesium.
Okay, so that's where we're at. Okay. So, we've got different types of bonding. We've got ionic and covalent. Remember, ionic has high melting points. Covalent are going to be some low, except for a couple of those giant covalent network solids like graphite, diamond, and silicon dioxide. Okay, so those are the 3 biggies that you really need to know about. Electrical conductivity, then, your ionics are they're not going to conduct electricity in the solid form, only when they're liquid or they're dissolved. And then covalent, for the most part, will not conduct electricity unless you're dealing with something like an acid. Solubility in water, then, the ionics, most of them are soluble. Remember your SNAP. Remember, the heavy metals tend to be insoluble. And then covalents, most of them are insoluble, but you've got a few, like your acids, again, that are going to be, or if they're very, very polar, they're going to be. Volatility. What does volatility mean?
Able to be stretched out.
No.
Is it the one that got counted?
Okay, so let's talk about vocabulary. So able to be pulled out into thin wires is ductile. Able to be pounded into thin sheets is malleable. Okay. Volatility has to do with vapor pressure. Okay. So let's talk about vapor pressure then. Okay. So when you have a sealed container,
Oh, like a soda can.
okay, so we're going to have a sealed container. This guy is sealed. And you've got a liquid in there. If you have something with low IMFs, that means that a lot of this liquid is going to go up into a vapor in here, and that's going to cause pressure. That's called vapor pressure. So low IMFs mean high vapor pressure, which is volatility. So if something has a high vapor pressure, that means it has a high volatility. T, to have high vapor pressure. Okay. If it has high IMFs, then it's going to have a low vapor pressure. Very little of this will go up into a vapor, and it'll have low volatility. Okay. So this has high volatility because these typically have low IMFs. Okay. All right. when you talk about an ionic compound, then you have alternating positives and negatives. That is what's going to hold that together. Now, if you happen to hit this like with a hammer, for example, it's going to cause these to shift. That means that you're going to have a positive and a positive and a negative coming together. What do you know happens with like charges?
They repel.
They repel. So this is why these tend to have very brittle characteristics about them. Because if you happen to like pound this with that hammer, you know, come down with a hammer and hit it, it's going to shift that and cause those things to break off. Okay. So that's what we're trying, I guess they're trying to show you with this slide. All right. Sodium chloride and magnesium oxide have exactly the same structure. The melting and boiling points are given here. Explain the values for magnesium oxide and why they're higher than sodium chloride.
Ionic bonds.
This has nothing to do with
Stronger lattice
IMX,
energy.
right?
Right? Why does it have a stronger lattice energy?
Hardness larger.
Right. You have a +2 charge here and a -2 charge versus a +1 and a -1. The charges are greater in this versus this one. Okay, were you able to get that on your, that was kind of an FRQ type one, wasn't it? On there? Okay. All right, here we are to hybrid orbitals. Okay, remember the way you figure out hybrid orbitals is you look for pi bonds. So for this, are there any pi bonds in here?
No.
So it's
Two.
sp3.
Oh,
Okay. Now, why is it sp3?
because
Okay.
there are three.
Because they're.
So when you have this hybridization, you've got a s, and remember you've got 3 p orbitals that are there.
You subtract
Okay.
each pi bond.
Yep. So for each pi bond, so when you merge these together, you merge these together into 4 sp orbitals. Okay. How many p orbitals did you use? 3. It's sp3. Okay.
And you got 4 because of the lone pairs.
Yep. Each lone pair gets 1.
That's 1 as.
You're using 3. You have 4 orbitals, but you're using 3
SP1.
or you're using 3 p's
Why are you using these?
because you have 3 p's. You're merging them with this s and making 4 sps
How do you know you have 3?
because you always have 3 p's
Unless you have pi bonds.
unless you have a hydrogen. Yeah. Okay. Well, you're always going to have 3 p's. It's whether you're hybridizing all 3 or not.
Because that would be.
Are we leaving or something? Is that why you're packing up? I don't understand.
Ends in 1 minute.
1 minute.
Okay, we need to talk about hybridization tomorrow then.
We don't have school tomorrow.
You know what I mean.